Hey everyone, and welcome back to this week's ML for Protein Engineering seminar. We're very lucky to be joined with two, potentially three speakers today, where they're going to talk about their new conditional diffusion model for applications to protein design. And we're really lucky because there's been a bunch of exciting updates since the last preprint. So definitely check out the paper if you haven't already. But today we have Kieran, Simon, and Francisco. So Kieran was a master's student at the University of Cambridge, and he recently joined industry. Francisco is a final year PhD student at Cambridge, or I guess he might have just completed. And he's been working on the interface of diffusion, stochastic control, and transport. And then Simon is a PhD student at the computer science department at the University of Cambridge, and he's interested in designing and engineering enzymes. So if you guys, I think there will be a little bit back and forth because we have multiple speakers today. If you guys just want to make a quick note on how you want to handle questions for the duration of the talk, I can always read them out to you. Or you can have people leave them in the chat, whatever you prefer.
Sounds good.
But
both, I guess. It's fine. People can interrupt, people can send questions, I guess. Whatever works.
Cool. Okay, awesome. So I'll let you guys take it from here.
Great. Yeah, thanks for the intro. And yeah, hi everyone. Thanks for having us. Today it's actually me and Francisco. Simon cannot make it on short time due to Wi-Fi connection issues in remote place, I guess. So I'm gonna cover for him. And yeah, we're excited to tell you about the work we did when we all did at Cambridge, where we did a framework for conditional diffusion modeling, and we had some applications for images, other things, and for today, I think most excitingly protein design. So about the agenda for today, maybe can you go one slide forward? Great. So we're going to talk about some background. So it's like, again, stating diffusion, proteins, giving a bit of ease into that. And then I'm just going to take over and talk about the actual framework. So how we're basically looking at these different approaches for conditioning, and how these pop out in different places, and basically how you can like think about this mentally and unify them in a one common framework. Then we're going to talk about the new method we basically developed on that, like a fine-tuning approach. It's based on this Doob transform paradigm, and show some results there with some other people. And then finally, we're going to talk about the results for proteins and give some recommendations of what we observe to work and what we observe to not work as well. Cool. So let's get started with the background. I guess the kind of classical protein design pipeline, I don't have to explain too many people here. Just shortly, like in many cases, you have some kind of design objective when you do protein design. Let's say you have a target which you want to design a binder, or you have a motif that you want to scaffold, or some other design constraints, most often, in many cases, structural in nature. What you then do is you want to design some backbone. Back in the past, what you used to do was like MCMC sampling with some kind of framework. Today, we use other approaches there. You get some kind of design backbone. And then from this backbone, because that's not what you can produce in the lab, right? You ideally want a sequence, so do some kind of broad-term optimization, some other methods, and get a pretty good sequence. And before you send it off to the lab, ideally you want to have some kind of guidance or some assurance that it's actually a good sequence, because lab experiments are expensive. So do some kind of energy calculations, some minimization, something else to get, again, some structural insight of if the sequence you produce is actually representative of the structure you want to get in the end. Today, basically, deep learning affects all stages. If you go to the next slide, you can see that like many of the stages are now augmented or sometimes also replaced by deep learning approaches. So the first stage is MCMC starting stage. Most people nowadays use generative models, for example, diffusion models, which we're going to talk about today. These backbone to sequence methods, we often use like message parsing neural networks and with folding methods like protein MPNN, for example. And once you have the sequence and you want to have some assurance of how good your sequence is, what people nowadays often do is use a structure prediction method, such as AlphaFold, and then do a self-consistency metric between the structure you designed for and the structure you generate in the end. Just look how similar are these. Go to the next slide. Today, we're going to basically mostly talk about this first part. So because that's often in this case, for example, where you're constrained, so your target comes in, or this could be a motif or something else. And that's basically the main stage where your conditioning plays a role. So that's where we're going to focus. Next slide. And diffusion models are kind of one approach how people do that. I guess you're all kind of familiar with the basic premise. Just to recap, it's kind of the idea is to do kind of denoising tasks. So during training, we noise our protein or image world our image. We ask the network to predict either the noise or the denoised image, and give the model both the noised image or the noised protein as well as the time step. So an idea of how much noise we added, to then go back to the unnoised version. And how people normally describe that, there are like different ways how people formalize that, Markov chain, etc., discrete perspectives, continuous perspectives. What we're going to look at today, what's going to be important for the framework is kind of the continuous perspective. So looking at this process, this both forward and the reverse one, as stochastic differential equations on SDE. An example for this reverse diffusion down there, you can see in this equation below, where x is our variable and xt is basically the random variable over time, where beta is basically a prefix parameter that defines our drift and our diffusion term. And what our network learns at training time is the score term. So basically the gradient of the log likelihood, or log probability, where you basically say, okay, guide me towards the regions of high probability given my data sample. Okay, I think there's a question. Yeah, good question. Why does this go from sequence to structure to sequence to structure? There are many ways of how this pipeline works, right? You can also just leave it with sequence, ignore structure at all. That's what many folks with language modeling nowadays do. I guess why traditionally people start with structure is because often, as I mentioned, these design constraints you look at are often structural in nature. You want to have like a target binder. So you basically think about, okay, how can we design something that binds to the surface? Or have a motif which I want to scaffold in three-dimensional space. So many of these constraints that people or protein and engineers think about when designing proteins or engineering proteins are structural in nature. That's why you start with structure. The second step needs to be sequence because that's what you in the end send to the lab, right? And in the end, the third step with the structure, it's not really needed. You can also just have some filters or some kind of quality constraints that just look at the sequence. Which often people find it useful to have some kind of structural idea again. So as I said, one metric people nowadays use quite often is self-consistency. So saying, okay, I predict the sequence, predict the structure from the sequence, and look how similar is it to the original design structure. And that gives me an indication of how good my sequence represents the structure I originally designed for. So you don't need to have this last structure step in theory, but people often find it useful as kind of a validation. Cool. With that out of the way, we can go to the next slide, I think. So this is like kind of the diffusion framework. And as I mentioned already, often we want to have some constraint, some kind of condition we want to fulfill. And one idea is, for example, motif scaffolding, where the idea is similar to image in painting. We have a subpart of a protein that we know is important for functions. Let's say a binding motif, a catalytic site, something else. But we want to scaffold into a novel backbone because, let's say, the natural backbone is immunogenic or too big for our application, or we just want a different secondary structure, etc. So in this case, for example, here, this purple part would be the motif and the rest around would be scaffold. And we scaffold this into a new protein. So the motif constraint should be kept similar or kept the same, whereas the backbone around is allowed to vary. And that kind of task is one of many design constraints. We can think of many others. I mentioned target binding. You can think about protein dynamics, where the paper on that, where we did that. So there are a few different things you can do. But for this presentation, we'll keep this as like our prime example in the protein case. Okay, so given that, you can think, okay, where does this also occur? Like where can we take inspiration from? And I really like this slide from a previous presentation from Brian Tripp and Jason Yim, where they basically compared it to the image in painting task. When there often is like the classical approaches, people had like 2021, 2022, when diffusion models came out, there were often these kind of artifacts you saw around in painting regions. In this case, you have this corgi that replaced the other dog. And you can see the interface, like the necklace of the woman or the girl is kind of blurry. The feet of the corgi look a bit weird. So at this interface between the person, for example, and the dog here, you often have these kind of inconsistencies. These artifacts we also observe them if we do like some of these earlier simple replacement methods, etc. in proteins, where like your motif is still conserved, your backbone looks realistic, but the interface is somehow off. And while in the image, that's not, I mean, it's not great, but also not a real issue. In a protein, that's detrimental, right? If your atoms are too far away, too close together, the structure just doesn't work and your metrics will fail. So similar to what people in image did, now the idea is, okay, what can we do in diffusion in protein space to do proper conditioning for motor scaffolding, but also for other tasks. So we had the project with some experimentalists at the time, which went through some motor scaffolding. And if you go to the next slide, basically we looked in the literature and got kind of, I won't say overwhelmed, but it was kind of a lot. There are many different approaches people took for that. And first idea was, okay, map out what's out there, right? What do people do? What can people manage? And how can we eventually, if these approaches don't work for us or are not good enough, how can we improve on that? So basically, there are many ways to condition diffusion models, and Francisco will talk a bit more about like how we can formalize that and think about this in more mathematical terms. But just to like an intuitive picture, basically. And in this case here, you can think of these blue blobs, basically, or these Gaussians approximately as your data density. So these are like data points, and your two axes, in this case, the vertical axis is kind of the motif coordinates you vary, and the horizontal axis is the scaffold coordinates you vary. In this case, these are like orthogonal because these are very like distinct, right? And if there's another condition, this could also be like not exactly 90 degrees, but in this case, we assume that. And we have this certain motif, X motif prime, which we want to conserve, basically. This is the one we want to have. So we want to sample from this distribution. We want to get good data points. So we want to get into these blue regions, but we also want to land on this line. So ideally, you want to end up in this lower left-hand Gaussian there. Or and if you do unconditional sampling, right, we start with random noise. So we start somewhere in the space. And ideally, our model learns the score well, and then gets to one of these peaks. But we want to get to the conditional sampling. So how do we do that? The different methods, one, for example, is replacement, where at every step in your diffusion trajectory, you just replace the part of your motif with the correct coordinate. So you guarantee that in the end, you will have the correct motif. But that, as I mentioned, often leads to these conditions where you have the correct motif, kind of a good scaffold, but the interface not great, or even your scaffold might not be that great, as in this like example case there. Another option, for example, is reconstruction guidance, like DPS and some other methods that use similar ideas, where the idea is you somehow predict where would I go completely unconditionally, which is our conditional model, and where would I go if I completely satisfy my condition. So basically these two axes. And we then somehow basically take a compromise between the two of them. And this is like a viable method for many tasks, but we can also, as this will later show, often this leads to this kind of tug of war phenomenon where you have this unconditional conditional update, and you have to balance quite delicately between the two. So you have kind of guidance scale that tells you how strong is one versus the other. And this is kind of finicky parameter. You always have to hyper tune, like a hyperparameter you always have to tune. Which gets kind of annoying if you do this for different targets, for example, where this varies and so on. So I hopefully show you like there's a lot of things you can do there, and they all look on the surface quite different what you do. You can also just directly train with your condition, for example. So what I will give over to Francisco now, and he will now explain to you how you can see this in a bit more unified way. And how we can formalize this properly so that we can later use this then for our approach application and see how we can improve on this method I just presented to you. So over to you, Francisco.
Thanks. Yeah. So let's start off with this. Oh, sorry, I lost the cursor. Okay. So starting off with Kieran left, we have this already reverse diffusion, right? Which samples unconditionally. So the first plot from the previous slide, right? Let's assume, just for the purpose of the talk so far, that we have access to this score, right? We either have the score or we have a very good approximation of it. We've learned it by a score network. And then what we'd like to do is we'd like to condition this stochastic differential equation to hit something, hit a number like the slice plot, hit a value at time 0, right? Because this process is going from time capital T to time 0, right? And there's machinery for this, right? Already existing in stochastic calculus, which is basically just adding a term to your already existing stochastic differential equation. This term is known as the Doob's H transform, and it looks a lot like a score. So the term in yellow that you can see here, right? It is, and we'll expand the term further down, but basically, you know, it is the gradient with respect to xt of log p of y given xt, right? And so this term comes out of an integral, basically. It comes out of integrating or marginalizing out 0 given t times the probability of y given x0. So you marginalize 0. And it's a hard term to estimate. So mostly we'll be talking about how to estimate this term. But for this particular SD that we have here, you know, if we add this particular term there, one might ask the question, okay, so what is the distribution at time 0, right? And it turns out the distribution at time 0 is going to be the probability of x0 given y, right? Of course, we have to pre-specify what the probability of y given x0 is, right? That might just be, you know, that a linear transformation times x0 is equal to a value. For example, the second coordinate of x0 is equal to the value like in the plot, or it might be a noisy transformation. A linear transformation plus noise is equal to a particular value, like in the noisy inverse problem setting that we consider in the paper. But anyways, the main point is that this gives us like a theoretical mechanism of just the term that we need to add, right, to be able to condition an SD. Something that's a little bit more technical that we don't discuss too much is that this SDE needs to start at the ending point of the forward process, right? So for diffusion models, the reason we don't discuss this is because for diffusion models, this is just going to be a Gaussian because the forward process just converges to a Gaussian. But if you're conditioning SDEs in general, you need to be a little bit more careful about this technical details and what X capital T is going to be. But for the purpose of diffusion models, we just started to approximate a Gaussian, so it's fine. So then, yeah, to give a more concrete example of what this, you know, y given x0 could look like, right? We consider the case like the motif scaffolding case or the image completion case where we have one of the dimensions or a subset of the dimensions are fixed, right? So we've got a delta likelihood there. And we would like to sample conditioned on some of these dimensions being fixed. And so we can see the illustration here of what, you know, potentially the H transform would look like, what the trajectories would look like. Oh, sorry, I got the mouse confused again. Okay, so how can we learn this H transform, right? Like, how can we find an estimator for it? And what we show in our work is, well, before going into that, let's kind of expand what the H transform looks like, right? So I have a mistake here. Sorry, I just realized there is a missing log grad on the second equality. Just omitted that there. But we're expanding the density here. And that density is just going to be probability of x0 given xt. That's the transition density of the backwards process. This is not something we have access to, right? It's a nonlinear stochastic differential equation. We don't know its transition density. And then times the probability of y given x0, right? What is the probability of y given x0? This is the likelihood we specify a priori. So if we're doing image painting or the motif scaffolding task, this is just going to be a delta centered on a subset of dimensions, for example. You know, for inverse problems, this will be a Gaussian likelihood of the form AX0 plus some Gaussian noise, where AX could be a linear transformation or some nonlinear transformation. And typically, like a, you know, prior work approximates this integral using moment matching on the transition density. So what does that mean? It means it approximates this particular transition density with a Gaussian. And then you're able to figure in, you know, you need to like learn, you need to, well, not learn, you need to estimate the mean of x0 given xt, and you just plug that in as the mean of the Gaussian. You should also typically estimate the second moment, but that's actually quite intractable, or non-computationally friendly, not intractable. And so, you know, the most common approximation is to just have an arbitrary variance, plug in the mean, this x0 given xt, which can be estimated using the score, something known as Didi formula, which we'll look at some point. And this is a really already quite well-known method, you know, reconstruction guidance or denoising posterior, diffusion posterior sampling, DPS. And it's been applied quite broadly for like inverse problems in imaging, you know, image super resolution, image inpainting, deblurring, yeah, among other things like phase retrieval, for example. A downside of this is that it's making quite a crude approximation, right? X0 given xt is highly nonlinear whenever t is a bit large, right? So we're going to consider values of t that are not necessarily just close to 0. This will evaluate at every time point. So at many points in time for large t, especially at the beginning, this is quite a bad approximation. And so we seek to improve on that. So what is not so difficult to show actually is that you can actually come up with an objective for learning this quantity, the H transform. And the objective is quite straightforward actually. It's just the score matching objective that we're already used to. But we have the score term. So if you look at the second term in the first sum here, right next to the blue term, that's just the unconditional score, right? So if we fix the unconditional score and optimize this extra correction term, then this will be learning the H transform, right? So that's what we're able to prove, right? The minimizer of this objective is the H transform, the guidance term that we need to do. So as long as we can simulate Y's, right? So for example, motifs, as long as we can generate maybe random patches of proteins or random patches of images that we want to unpaint, then we can just use this sort of fine-tuning objective, right? Let's go to the next slide to make it a little bit more clear. So, you know, in practice, we never have access to this grad log PT, the unconditional score, but we do have access to a pre-trained score network. You know, for actually most of our experiments, we just download one that's already pre-trained by other papers. So that's what epsilon theta star is. That theta is fixed. We're not optimizing with respect to theta, and this is just a vanilla score matching objective here, right? But all we're learning is this guidance scale, right? So it's almost as though we're training a conditional diffusion model, but we're only learning the guidance scale term and keeping the unconditional component fixed. And yeah, this, in theory, this should learn the H transform, although it takes a little bit of tricks, which we'll discuss in a bit to actually get it to work. One thing to also mention is, you know, if you weren't learning only if you aren't only optimizing over phi, but maybe you optimized both phi and theta, this would just be doing conditional score matching, right? Well, we also call this amortized training because you're amortizing over all the different conditions. And this is a little bit akin to classifier-free guidance. It's still different. And actually for protein tasks, we have found this to perform quite a bit better than CFG. Don't know why CFG doesn't quite hit the mark in some of these tasks. But yeah, this is to, you know, illustrate how another semi-well-known approach just falls out of the H transform framework, falls out of the same objective that we're considering. So yeah, to illustrate things a little bit, we talked about Tweedy's estimate. What Tweedy's estimate is just a way of estimating x0 given xt. And, you know, for an unconditional diffusion model, x0 given xt is just equal to x0 hat, right? Which is just the score model plus the prior drift. It's scaled in certain ways. So you can estimate x0 given xt quite, you know, straightforwardly. Basically this equation here using the score, the pre-trained score network. And here we just write down Tweedy's expression for the conditional setting. And when we get, which is quite nice, is we get the Tweedy's expression for the x0, this x0 bar is basically Tweedy's for the unconditional model, minus this correction term, this guidance term. So it's a nice way to interpret the H transform. You know, as expected, some people do just call it a guidance. It does just kind of correct the direction that you're going in. So a little bit, you know, more on the conceptual side is we are able to kind of reformulate this H transform learning objective in many different ways. And actually some of these ways are, some of these reformulations are actually really well studied in other communities, such as stochastic control, sampling, optimal transport, etc. So in particular, the interesting formulations here are 2 and 3, I guess. So, well, I mean, 2 is not interesting. 2 is the one that we've already discussed so far, which is the main objective that we explore in this work. But 3 is an alternative objective that doesn't require pairs. And we do explore this in the appendix on some like maybe small scale tasks. So the minimizer to this objective here also learns the H transform. And this objective does not require generating XY pairs. You know, before we have to like generate an X0 from the data and apply the measurement operator, whether it be, you know, slicing some of the dimensions away that we can't see them anymore for imaging painting, or be something more complicated like blurring the image or something like this. The objective in 3 does not require this. Another thing that the objective in 3 is maybe a little bit interesting for us was that it provides a link to a lot of work in sampling and MCMC, right? The task there is a little bit different. You don't have data. You just have like a Boltzmann distribution. You want to generate samples from it. The objectives used there to leverage diffusion models in this context of the non-data driven sampling are of the same form as what we see here in 3. They call them stochastic control. They're basically just reverse KL objectives. And, through this link, what we kind of took out of this work is we looked at some of the architectures that have already been developed in the sampling/diffusions community. And most of these architectures, what they have is they have an extra term, which has a neural network that only depends on time, multiplied by a cheap estimate of the H transform, right? Basically like a Tweedy's type of estimate, a DPS-styled estimate of the H transform. And so they didn't call it a Tweedy's estimate, but you can actually show that the thing they use here is just usually log grad of the target distribution is more or less a cheap like Tweedy estimate. So adding this, you'll notice that we are taking gradients with respect to x0 hat and not xt. It would be too slow if we did xt. Doing with respect to xt, which is what is called DPS, would be more accurate. But given we're learning this whole network, it doesn't matter too much. This just helps give a good initialization, a good starting point to our optimization objective. And we did quite a few ablations in the appendix, and the difference that this term gives, plus also passing x0 hat to the network so that they have knowledge of the unconditional network's predictions capabilities, improves things massively. I think without these inductive biases, the results are reasonable, but they're not competitive. So this architectural setup was very important, and a lot of it came through like realizing the connection to methodology and sampling. So this bullet point 3 here in this result. So now we're gonna like look a little bit more on the practical side, like the actual results that we obtain. So, I mean, this is just a more pictographic version of what we just discussed, right? So our objective, our neural network architecture comprises of 2 terms, right? One term, which is the main network that's learning the nonlinear aspect of it, which depends on xt. It depends on x0 hat, right? Which is just the E of x0 given xt Tweedy's estimate. And it also depends on a cheap estimate of the gradient, although most of the experiments that we realized that didn't help too much, that third argument. Plus this kind of cheap DPS or this cheap Tweedy's terms, which it doesn't really add any compute. All these terms have already been computed effectively at this point, so it doesn't slow things down. And yeah, that's mainly it, right? We using this as a neural network architecture, we fine tune a conditional diffusion model. Why do we call it fine tuning? Just going back a little bit. We're only learning a smaller network, and the name of the method is efficient fine tuning, right? Doobs, it's sort of like a parameter efficient fine tuning approach. We're only learning this extra additive network, which in our experiments is actually really tiny. We do 9%, maybe some of the largest are 9% of the original score networks in size. So they're significantly smaller than the epsilon theta star network. And this is why it's very parameter efficient. So we only learn this small network on just a conditional training objective. That's what we call our method deft. And we run it across quite a big suite of image experiments. So for example, this one is, it's like image in painting, but if you can see like the top corner, it's very irregular masks. It's not your usual little square masks. These are like randomly generated masks from the Reddif paper. And we compared to all the methods in that paper. So we compared to DPS, as well as a few maybe faster variants of DPS like PyGDM. Well, not faster variants, but faster variants of reconstruction guidance, not DPS. And we found def to like significantly outperform a lot of these approaches. So yeah, one of the tasks where we see like the biggest gap actually, so there's another task which is a non-linear deblurring. So you have a neural network that's being pre-trained to blur images. That's your measurement operator. That's how you generate your Ys. And here the task is to undo this. And here, like in these nonlinear tasks, so we consider 2 different tasks, 2 different types of tasks: linear inverse problems like image in painting or just traditional blurring, and nonlinear tasks like phase retrieval, nonlinear deblurring. And we find our results in the nonlinear tasks to quite significantly outperform a lot of the existing methodology. So yeah, here's looking, okay, so these are the linear tasks. And in the linear tasks, I think we're probably quite tight with, I'd say, Reddif, and these tasks are, I wouldn't say they're entirely solved, but the results in general are pretty good for state of the art. So, there's not an incredibly huge gap there to narrow between methods. Whilst in the nonlinear tasks and in some of these more complicated data sets, like, sorry, I'm trying to remember the name, like computer tomography kind of tasks, we do find our method performs significantly, right? So here, the HDR task, sorry, this is like, again, another nonlinear one, phase retrieval coming from like signal processing kind of tasks, and the nonlinear deblurrings, we can see like the performance differences from def to Reddif are quite significant and across the board quite uniformly. Another thing to point out, which I just forgot, is that if you look at the last column, it's really quick to train our approach, right? So we train, I don't quite remember the exact numbers, but we train on a very small validation set, right? It's again like similar to like our parameter size. It's something like 10% smaller for these tasks, for the image tasks, something like 10% smaller than the original training set of the methods. The network is also very small, and as a result, like actually, if we add our training time to our inference time, we still actually are faster than Reddif's inference time only, or than DPS's inference time only. Because at test time, our method is incredibly fast. So the only bottleneck is training, but even the training bottleneck is still quite faster than a lot of the previous works that don't actually have any training, but in a way, their methods do kind of train at inference time. One thing we found like an interesting pattern across all the experiments is, like I showed, like the neural network architecture has this N and T term. And this is not our nicest plots. I think in some of the easier tasks, the plots are a little bit prettier, but you can still see the pattern here. So what's kind of happening here is that the plots, I think the axis is flipped, but basically the closer you get to the target distribution, the closer you get to generating the data, the more this N and T scale seems to get closer to 0, right? Because you don't want to add too much noise as soon as you're close to the data. So this is automatically learning a guidance scale for the second term. And the guidance scales are quite intuitive. Like if you were designing a guidance scale, this is kind of what you would do. Like you would, for the first steps, you'd kind of like maybe not turn it on so large. And then as you're more confident about your generation, you start to tweak this up. So we thought it was quite a nice signal that this thing is automatically learning the guidance scales that we were already kind of having to tweak for some of these problems by hand. And it was really tedious to do a lot of this tweaking. Okay, yeah, I'll hand over to Kieran at this point.
Cool, yeah. After this dose of framework, we're basically going to look at, okay, just showed some really cool results for the nonlinear and linear tasks and images. And now the idea was, okay, what do we do for proteins? Because that was the original motivation where it came from. And images are always nice because it's a lot easier to validate things. So like quicker to iterate, quicker to test things, do a few things. The metrics are more standard, etc. But then we're like, okay, the original motivation was we want to like do these tasks with proteins. So what are we going to do there? If you go to the next slide. The key question is basically, okay, we have this H transform paradigm of like, okay, we have like, can like unify a few different approaches, and now we have this new fine-tuning approach as well. We want to say, okay, can we use this to like scaffold backbone motifs better? So with the idea, okay, backbone scaffold now means obviously alpha backbone. We chose that because like many different methods, depending on Gini, diffusion, depending on which diffusion model you want to use, they all kind of agree that like if you give a C alpha, you can use that basically. So we want to keep this common denominator there. Okay, so let's say we want to now use this. How do we do that? As Francisco said, in the image case, we just download a pre-trained model. And then the main thing we do is we have this small, teeny tiny adapter network. Like some of you may have done some LoRa, for example, or some other adapter methods in like language models. The idea is quite similar. So you don't add our weights here, so like the exact mechanics are different, but the idea is you have a big pre-trained model, and depending on the task you fine-tune for, you have like this small adapter that you add on. So the natural question here was, okay, which Bayes network do we use? And while in the image case, that's kind of an easy choice because they're like big leaderboards and like a lot of iterations gone into, and the kind of field has, I wouldn't say calmed down. There's a lot of publishing happening there, but there are kind of a few standard methods that work quite well. I guess in the protein diffusion space, there's kind of a lot of stuff going on. So when we, in the last 3-4 weeks, there were again 2-3 new papers in the space with new results, better methods, etc. So when we started this work, so let's probably finish this slide. When we started with this work, we needed end of last year, I think, summer, like mid last year, something. We really needed to choose one method here, and we chose Genie, like a method from the Akarashi lab in New York, Columbia. It wasn't the most performant method model available, but basically our idea was we wanted to like be fast to iterate and basically fast to train, because we want to do some retraining approaches, fine tuning, etc. And we want to be able to hack that thing. So we want to like try a few things, add some like DPS guidance thing, add our fine tuning approach, etc. So we want to have like a kind of nice documented code base available, which was the case here. And it was kind of smallish with our resources was still available to retrain and do some things there. And we then wanted to test on the RF diffusion benchmark. I saw there was a question. I think the question was, can you clarify the difference between the and classifier guidance? I guess Francisco, you can add on that, but I guess in classifier guidance you have a classifier, right? It's like you
you can't train a classifier if your y is real valued, right? So a classifier guidance trains probability of y given xt, right? And in our case, what is y? Y, for example, is an image with some missing values, or y is a protein, or y is only a tiny segment of a protein, right? And some of the other cases, y is the spectrogram of an image. Not really. So you can train a regression model with a Gaussian likelihood, but that gives you a Gaussian density for something that is not necessarily Gaussian, right? So why would probability of y given xt be Gaussian? That's a strong assumption, right? So what you can do is you can try to train a normalizing flow on that. That comes with its own difficulties, right? So again, classifier guidance is only something that's very natural when you're training a classifier. If you're just training a Gaussian likelihood, you will realize that your density is just going to be a mean squared error, and you're back to something that looks a lot like DPS reconstruction guidance, right? So you're making a very weak approximation, right? You could try nonlinear density approaches, like some of these, autoregressive normalizing flows and things like that. But yeah, I mean, that'll be its own thing. That's not classifier guidance anymore. And would that work? It would be its own method. It'd be quite tricky as well to train a flow for that density.
I agree. I think the classifier guidance approach makes sense if like your y is some kind of like class label. Let's say you have images and you have like ImageNet or something, or you have like a clear classifier for that, so like what that is.
And here's the thing, I can very trivially prove to you. I mean, if you look at the integrals further up in the slides, the probability of y given xt is not a Gaussian, right? It's an integral or a convolution between something that is highly non-Gaussian and a conditional Gaussian likelihood. If you train a regression model with a Gaussian likelihood, you're making an incredibly naive approximation. You're going back to DPS, which is what we wanted to, in some sense, improve on. So really only like the classifier sense is the one that comes naturally as a good approximation. And in these settings, you can't quite do classifier guidance, right? Presumably, I think that's why people have not done classifier guidance for inverse problems.
Also, as we've shown, I think Francisco showed these linear, nonlinear tasks. I guess, especially if you're in a nonlinear setting, like you're highly non-Gaussian, then like you also see that these methods, DPS, etc., that have this Gaussian assumption fail quite badly.
So in the nonlinear settings, the probability of exactly. It's you're even a bit more non-Gaussian there. But in both settings, even the linear ones, it's probability of y given xt is still non-Gaussian. So you don't want to make the approximation. It's nicer to just learn, the score is just a nonlinear function. Why don't you just learn the score directly instead of learning the density, which is the big difference. Classifier guidance learns the density y given xt. We're learning the score of y given xt with a neural network directly, no Gaussian approximations.
Okay, I think was an example of the Gaussian.
I mean, you can, right? But a regression loss is going to be Gaussian, right? So if you want to learn something more general, it's going to be a normalizing flow. And there you have a new paper. You need to comes with a bunch
I
of.
was going to say you basically shift the problem, right? Like solving.
Sure, you can learn a conditional density. That's completely valid. You can learn a conditional density on the y's given xt, and you'd have to use something like a normalizing flow. Otherwise, you're back to, if you just use a regression error, you're back to a Gaussian assumption. Yeah, so you definitely can do that, but that wouldn't be that wouldn't be classified for guidance anymore. That would be a new paper that you could work on yourself. It's a good idea to try out.
Does that make sense? Okay, someone else asked, do you consider the unique property of the protein data set? Will you tell me how do you incorporate that during the design of your algorithm? You mean doing the pre-trained network basically we take, so this kind of the Gini model itself takes care of that, right? Oh, wait. When data sets are different than pictures. Yeah, exactly. You're right. And that's basically the main thing we also found when using GPS and other approaches, right? Especially this guidance scale was kind of, I think in image cases, you often find like a kind of compromisable guidance scale that you can choose for like a few different tasks. For proteins, we found this to be very highly non-trivial to find like a unique guidance scale that works for all these approaches. For just like these inference guidance approaches. So yeah, we observed like very strongly that like the properties there were different. And that's what motivated us in the end to not use just a pure like guidance approach, but to use this fine-tuning approach basically to adjust your network to that. The fine-tuning algorithm structure that Francisco showed, we took that for proteins as well. I will show some limitations of that later on, basically in the naive application. I think we have some ideas of how we can improve that further. But basically what this boils down to is you have basically this small network, it's a adapter network. And ideally you'd want to share some weights between these two so that you don't have to learn. In our case, you can see in the G network here, we have this invariant encoder, we have this equivariant decoder, and we have this latent space. It's kind of similar to AlphaFold style with a single and a pair representation. We basically took the naive approach here and just made a tiny version of that for our fine tuning. Ideally, you wouldn't like completely train it from scratch very tiny, because then the geometric bias, the invariant encoder and the equivariant decoder become somehow limited at some point. Ideally, you'd somehow reuse them and then just like basically smallify or like basically make the latent space smaller. So that's something which maybe in plan for now. Yeah, so that we observe differences, but the main algorithm framework basically is the same. Short answer. Anything to add, Francisco? Otherwise,
no, I think yeah, you
cool.
should go on.
Cool. Then what was the time? Okay, sounds good. Okay, we use Gini small model. I think by now there's Gini 2 out and others, so you'll probably improve that by using a newer model. But we just basically want to get, okay, how far can we get with fully amortized training versus how far can we get with our super cheap fine-tuning approach compared to that. Okay, so we go to the next slide. That was kind of like very stylistic. Next slide, we have some numbers, but basically just like to illustrate the problems we mentioned before. With in-painting, with this replacement method, you are guaranteed to have your motif at the end, right? That's what we discussed. At every time step, you just insert your motif coordinates and do that for the whole training process, do the whole inference process, sampling. And while your motif is then perfectly reconstructed, you often end up with, you can see on the left there's this chain break. On the right, there are like really unstructured regions there. So basically, you often end up with just like boundary problems that I mentioned at the start. Reconstruction guidance, again, like you get nice proteins, but your motif really doesn't fit that well, or the other way around. There's this tug of war I mentioned, like guidance scale tuning comes in again, which is really annoying. Of course, if you do amortized training, so if you train from scratch, basically, your model false conditional task, now okay, like motif scaffolding, and you get quite nice results because your model is basically literally trained for that. So your whole training budget was used there. And as Francisco said, this is not what we do there in the paper is not directly CFG, so there are a few tweaks to that, but maybe the main idea is like amortized training again. And you don't want to dwell on that too much. You can just go to the next slide. which basically is just some comparison of that to diffusion on this benchmark of like contiguous motifs. So motifs that like span one subregion. And here the success metrics are basically similar to what diffusion and all these other papers basically say. So like if you want to have like the self-consistency RMSD, as I mentioned, where you have the structure you design, the predicted structure, you want this be similar. You also want your motive to be similar, and you want to be a bit more strict on that. So 1 instead of 2 angstrom. And you want your prediction, so your AlphaFold prediction or ESM-fold prediction, what you use, you want this to be confident. So you want your PLDT and other things should be confident that the structure is actually what you think it is. So if you apply these metrics basically and like 100 samples and then say, okay, how many of these samples, how many percent? So if you do 100, how many of the samples have a success rate? You can see in these tasks, like I don't remember the exact numbers, but I think with like 1 to 2% of the training time or something, and like maybe a few percent of the parameters there, we already have like kind of okay performance compared to like art diffusion, which like at the time was like the state of the art method. Okay, Danny, this in silico success, exactly. So in silico success rate is exactly what I defined on the right there. So these like 5 different criteria. So you have a sample, so a generated backbone, you fold that, you inverse fold that with protein NPN, you get a sequence. You fold that again with a folding model, and then you calculate these 5 different metrics. And if basically this thing satisfies these 5 different metrics, then it basically counts in silico success. So if your backbone is similar, your motive is similar, and like the AlphaFold, or in that case, the metrics satisfy these constraints. Exactly, consistency, yeah. Cool, so we already observe, okay, this is basically the roof line we can get with this model because we trained amortizedly, right? It's like this model is completely trained for this task. But now the interesting thing is we said, okay, how can we, this is kind of, in this case, it was relatively easy to train because it was a small model, but we want to extrapolate to the setting where we have a super large pre-trained model. I think we're slowly getting there, like more and more people build these really large models in protein space. And it's going to be more and more important to have like, if you have a custom task, to basically be able to fine tune on that. So let's say, okay, let's say we couldn't retrain this, we couldn't do this amortized training. How could we now fine tune that? Let's go to the next slide. That's basically just like, again, the image that Francisco showed before of our depth approach. The idea is, okay, ST theta, so this purple box there is now our Gini model. And we now want to make this mini tiny HT pi there, which is our small fine-tuning model then. So it's basically, the rest is exactly the same as before discussed. So you can go to the next slide. And as I mentioned, we just made this Gini model very, very small, and then tried a few of these different tricks. We basically went forth in images and proteins, the different input terms which showed, different initialization, etc. What we basically saw, I think the small model is 3 or 4% of the original model. So where Gini was already quite small. So 3 or 4% of that is even smaller. And the medium model was, I think, 8 or 9%. It was still quite small. And you can see, we can show the metrics later on, but compared to DPS, it still outperformed that by quite a lot. So you basically, the DPS, the best sample here, there's a lot of chain breaks with this weird, basically chain distances, which doesn't really work. Whereas depth also has like, I think the medium model got it quite right. I think the small model still has like chain breaks there, I think, but it's generally looking a lot better than DPS in that case. And this is a single example. I can show you numbers later, but basically, if we look through a lot of samples, we calculate the metrics, and the patterns are basically similar across tasks and samples. So if we go to the next slide, while basically it improves a lot upon DPS and other these like inference time methods that Francisco showed before, it doesn't match the amortized performance. The amortized performance gets this often quite often, which kind of makes sense, right? We completely trained from scratch for this specific task. If you go to the next slide, basically this is like the common pattern we see. So you have like the amortized training, is kind of the purpose-built thing, right? You cannot always afford that, but if you can afford that, it's the kind of gold standard. The fine-tuning often gets really, depending on the task, as I said, like in non-linear tasks, it's often a lot better than DPS approaches. But even in motive scaffolding, it outperforms them quite a lot. Whereas these like inference time guidance approaches, depending on what you do, often kind of suffer from some problems there. Okay, next slide. This is like an example of, look at the time. Maybe I'll just give a few of these slides to just like get the end, but just this slide, for example, because Danny asked about that. This is basically just a scatter plot of two of these metrics, the main important ones. The horizontal axis is the SC-RMSD, so how close your structure to what you predict it to be, and the y-axis, the motif RMSD. And you can see that while the amortized basically is like, has this nice bottom part where like this quadrant in the lower left is where you want to be, so below 1 in the motif and below 2 in the backbone. You can see that the depth model has some that kind of, it also clusters in this lower corner, but it doesn't quite reach these thresholds often. So we have like 36% designable for amortized versus 28% for depth, which is lower than 29% for 4%, which is a bit lower. But if you imagine that you have to pre-train this whole model from scratch versus just a very small adapter on top, this can be worth depending on how expensive your model and how important your task is. Okay, I think we can skip to the next. There's a few more examples of that. This like the evaluation on this benchmark there, where like green is again the amortized training, black is the DPS paper, the DPS approach, and depth is then 4%, 9% model. You see this blue and orange bar there. You can see that like in most there are actually just a few things where DPS actually solves the problem here, like gets some successes. Whereas depth actually gets like success in most cases where amortized training also gets success. It's always a bit lower. But as I mentioned, you have to think about like what kind of training performance versus what your inference budget is. So for us, that worked quite nicely in that setting. Next slide. Questions? Okay. So as mentioned at the start, there are a few common limitations which you can improve on, I guess. So in our case, like Genie is a nice architecture because like it's really well documented. We could take a lot with it. But I use like some things from AlphaFold, for example, triangular updates for those people that may be familiar with that. They have like kind of cubic runtime, which can be really annoying when you want to do sampling. So it's kind of very slow often. And as I mentioned, we focus here on contiguous motifs, but we also did some experiments on non-contiguous ones. We can basically just extend it to that setting. Contiguous meaning you have a certain stretch of motif that are not necessarily residues next to each other, but there could be different ones. Conceptual limitations there, I mentioned that already, like this fine-tuning has a small model. Right now, we just use a completely unified, like minified version of the Genie model. So with its own geometric encoder, their own geometric decoder, with its own IPA, etc. And that basically needs to learn its own geometry there. The time constraints just couldn't do more there. But ideally, what we were going to do, similar to images, right? You'd have like this shared embedding space, and just in this embedding space, do that without having to pre-train, like basically train the encoder and decoder from scratch again. And yeah, we also another thing we saw was quite interesting. Like there's not a linear performance gain just making the thing bigger. So it's not this, if you make it like 100% size, you get like 100 times the benefit with 1%. It's also not even monotone. So you don't see 9% is sometimes worse than 4%, which is also quite interesting and shows that even the 4% model, as we saw before, gets quite good results in many cases. Okay, next slide. So yeah, basically from that, like a few future directions, you could swap the base model to like faster sampling times to get this a bit more accelerated. Ideally, you're trying to share this encoder and decoder architecture. And as I said, you can increase the training budget for the fine-tuning model, not just the size, but only just the steps. I mean, Francisco mentioned at the start, like data size, like limited, partly to computational constraints, partly to show that it just works with limited data, and also just in like training steps. I think we trained this for like few hours, I think. So it's like very, very short compared to these base models. So you can also like improve on that front. And also, as Francisco has seen, these non-linear tasks have worked quite well in images. And we have a few non-linear tasks in proteins as well. I think I mentioned like we have this paper on dynamics and on other approaches. where I actually have like nonlinear tasks in the protein setting as well. So it'll be quite interesting to see how the performance there works. Okay, I think, can we go to the next slide? Cool. I think we need our time. I just want to give a short shout out to Paul too. We can skip that, but they also have some fine tuning. It's a bit different to ours. They basically fine tune the whole model. But there's also some cool results in this. Just want to really give a shout out so you can have a look at that as well. They use something called reinforced fine tuning, which is a very similar acronym in the end. But they use that to basically, in their case, look at secondary structure. So they fine tune another example use case you could think of. We did for motifs, but they did for secondary structure. So you want to have a model that not only produces alpha helices or beta sheets, but some mixture, ideally. And via like fine tuning a specific data set enriched for that, they were able to get that. I think you can skip the next slide, just for time. So they show this for a lot of proteins. It's quite cool. Check it out. But I think we can go to the summary slide then. So I'm out of time, or some time for questions. So yeah, takeaway recommendations, what we got from there. As I said, we're still in contact with some people on testing this out, but just from the in silico metrics alone, you can basically see like, okay, if you know a condition ahead of time and you're completely training a model from scratch, then amortized conditional training is kind of the gold standard. You can do that with your condition. But if you use a pre-trained model, or if you don't know that, then I think like the depth approach, this fine-tuning, is quite cool when you have wanted the sampling efficiency, and you have like a small fine-tuning data set which you can work on. If you don't have this fine-tuning data set, then there are like this inference guide methods, and there are also some cool improvements there. So just want to mention like TDS, for example, is a really cool paper that does some work there on improving these. I think if you have this like specific fine-tuning data set on which like you want to have some properties like secondary structure or motifs, which you want to fine-tune, I think it's really worth giving the depth method a shot there. Cool. So in summary, if you put the next slide, basically there's this trade-off. We observe in many cases between flexibility and performance, right? If you want to completely pre-train a model with amortized, you have kind of a lot of like hit on your flexibility, but you get good performance. And I think that is kind of a nice sweet spot there where you can try a few things and see how flexible and throw out different heads, but still kind of okay and becomes really good performance. And yeah, hopefully we convinced that in this case, theory syndrome is quite nice with method development. So a few of these hacks, like the hex architecture decisions, like this time-dependent guidance schedule and some of the inputs were coming from theory basically, and it turned out to help quite a lot with our method in the end. So yeah, thanks a lot for your attention. I think we already have some questions in the chat. I think you're answering these, Francisco, right? Okay, yeah, I see.
Yeah.
You mute. Okay, yeah.
So I couldn't find
cool. Yeah, shortly acknowledgement. So like Simon couldn't be here today, but he also contributed message to this work. Also with Alex and Shreyas, who did a lot of the work on the image examples that Francisco showed. Also with Ricardo and also Vincent and Emil, who were also involved in the first part of that work, and some valuable help there together with Julia. And yeah, Pietro, our supervisor, who supervised on that work. Yeah, hope that was like kind of a nice forward overview of both the framework, how you can like view diffusion from this conditional perspective, and how you can also use that to design like practical methods on that. Yeah, if there are any more questions, I think there are a few in the chat that are being answered, but if there are any more questions, feel free to either speak out or send in the chat, whatever works for you, I guess. But yeah, thanks for listening.
Awesome. Thank you, Kieran and Francisco, so much for giving this great talk. I think there was definitely a lot of questions in the chat throughout, so it was great to go through them. Definitely encourage everyone to reach out to, or it seems like Meg has a quick question. Okay, so we'll take this last question from Meg, but definitely encourage everyone to reach out to the speakers offline. Their information will be on the website and on the slide over here. And then the recording will also be available on our YouTube page in about a week.
Yeah, sure. Okay, so let me have a look. It's a good question. So let me think about it shortly. So you're talking about like non-canonicals here, right? I think it's not necessarily like a size constraint. So I think the size isn't the main problem here. I think the question is like, I showed you like the generative methods. I mean, in our case, for example, Genie works on C alpha atoms. So the C alpha atoms in theory don't really care about what your citation is, but I guess your model is trained on canonical amino acids, right? And especially your whole pipeline. So like the inverse folding and as well as the folding mostly works for canonical amino acids. So I think that will be the limitation here. I think we see more and more of these all atom methods, both for the diffusion model, but also like ligand MPNN now coming, AlphaFold 3, right? That predicts complexes with like other things. So I guess in that setting, the method itself is quite agnostic, right? So it doesn't matter really if your condition are the alpha atoms or if you're full atom structure. So I say if you make the switch to these to all atom models, and you have some data on that, like a data set, then I think it should in theory be possible to do that. Yeah, I think that'd be my answer. And again, like because like more and more of these models are coming, and I think in tendency they're getting bigger, so it can, I guess, fine tuning is kind of applicable there. Cool. Yeah, I think as I said, like a lot of the questions, I think a few long ones have been answered in the chat. Otherwise, feel free to shoot us a message. I think my mail is actually not valid anymore, but my Twitter is still, and Simon's email should still be valid. So shoot us questions there if you want to, or on Twitter. And yeah, happy to chat anytime otherwise.
Amazing. Okay, thank you guys so much, and we'll see everyone in 2 weeks then.
Thank you.
Cool. See ya.